Right. So it is one of the most important uh, instrument, that is spectrometer. Right. Frequently they have asked questions regarding spectrometer, and many students don't have a clear understanding of the apparatus because it looks a bit complicated, right? But today I will explain you the spectrometer simply once and for all, right? Okay, so in the practical book it is 19 and 20, 19 and 20. So here we are going to first we are going to adjust the spectrometer, right? So that is the difficult part. So once you adjust the spectrometer, you can easily take measurements. You can easily take, measure angles, right? So this using spectrometer, you can easily measure angles very accurately. That's why this instrument is important, especially when it comes to experiments regarding light, right? Regarding light. Okay. Under spectrometer, right? Adjusting spectrometer. So that is what we are going to discuss first. Then we are going to measure refracting angle. You know the prism angle? That is capital A. Then third, you can measure angle of deviation. Using a prism, you can use angle of deviation. We call that simple D. You can write this with me, right? Take a note. You can write this with me. Then fourth, we are going to measure angle of minimum deviation. That is capital D. Okay. So that is what we are going to do. First, adjust the spectrometer. Once you adjust it, you can measure these angles. Refracting angle, angle of deviation, angle of minimum deviation. So that is what we are going to do here in this part, right? So a bit lengthy experiment, right? But bear with me, this has so many marks in the exam as well, right? So this is how this is simple sketch of the spectrometer. So in the spectrometer, it has a prism table. Some of you might have used this in the school. Anyway, it has a prism table like this. If you want, you can draw this with me. It is attached here. You can actually rotate the prism table around this bar. Then here you have a telescope attached. From this side, you have a telescope attached. So it is like this. We call this telescope. It is a usual telescope, right? I think you have learned telescope. We can name it as, we'll say telescope. Or we can name it as capital T, right? Just a telescope which has an eyepiece and an objective piece. Then another part, to the stage of the spectrometer, there's a collimator. We call this part collimator. It also is we call this collimator. This is prism table, right? Prism table. From now on, I'll call this P, right? Collimator means capital C. You can take this down. So we have a collimator. prism table, and a telescope. So the telescope just has a objective lens and a eyepiece. I think you have learned telescopes already, right? Under optics, objective lens and an eyepiece. Then you have the prism table, capital P. Then there's the collimator. So the collimator is a new instrument. Collimator is just, it has a lens here, only one lens, and at the other side it has a slit. Slit means a thin opening, right? When you look, if you look from here, it is a thin, slit, just an opening, right? Thin opening. We call that a slit. Actually, you can change the size of this slit using a screw here. You can rotate a screw, then you can change the size of the slit. When you are doing the experiment, this slit has to be very thin, as much as possible, right? Okay. So this is a simple edge case of the spectrometer. Images of a real spectrometer will be given on that PDF, right? If you check that. Okay. So besides these, there are screws attached here. For an example, this telescope, actually you can rotate this telescope around the prism table. Prism table also can be rotated independently from the telescope. Prism table and the telescope can be rotated independently from each other. But this collimator is fixed to the stage of the spectrometer, right? It is fixed to the stage of the spectrometer. They ask these in the exam, right? Only prism table and the telescope can be rotated independently. But the collimator is fixed. It cannot be rotated, right? It is fixed to the stage. Okay, did everyone draw that? Thumbs up if you have drawn it, right? So as I'm explaining, just take notes, right? We don't have that much time for you to take the note. So as I'm explaining, take notes, right? Okay. Everyone, did everyone do this? Thumbs up, right, if you have. Right. Under this, write down prism table, capital P, prism table, capital P, and telescope, capital T, can be moved independently. Prism table and telescope can be moved independently. Then to the same line, write collimator, capital C, is fixed. Collimator, capital C, is fixed to the spectrometer stage. So it is like this, right? So you have the collimator here. Then you have the prism table. Around the prism table, this telescope can be moved. like this. From this side, this telescope can be moved 360 around the prism table. So is the prism table. But the collimator is fixed, right? You can draw this as well. Okay. Then we'll move on to how to do these adjustments. Adjustments is somewhat hard part, right? So you have to carefully listen how to do the adjustments to the spectrometer. So there is a order when you are doing adjustments. First, you have to adjust the telescope. First, you must adjust the telescope, then collimator, and finally you have to adjust the prism table. You cannot mix these up, right? You will understand once I'm done explaining this why that is. First you have to adjust telescope, then collimator, then prism table. You cannot mix that order, right? Below that, write order of adjustments. Order of adjustments, right? First one, write down telescope. Second one, write down collimator. And at the end, finally, prism table, capital P. You will understand why that is once I explain these adjustments, right? Telescope, collimator, and finally, prism table. Okay? So first you have to adjust the telescope. Write the subtopic telescope adjustment. Let's see how to do the telescope adjustment, right? So what do you mean by adjusting the telescope? So this is how the telescope is made, right? You have a objective lens in the telescope like this. Then in a separate tube, I mean pipe, it includes a crosswire, something called crosswire. You have seen when you look through a sniper, you can see two lines, right? Two perpendicular lines. Those are called crosswires. So here as well, you have these two crosswires, right? But it is in a separate tube. These can be moved independently. That's why then inside this tube, you have the another lens which we call eyepiece. Then it is closed here. So there are two pipes, I mean 3 pipes actually. You can change these independently. There are knobs and screws to do these changes, right? You can refer that PDF and identify those screws. I'm not going to explain those as well. Then you can look from here, right? You can look from here. Okay. Below this topic, write down. I'll explain after that. Below this topic, write after adjustment. After adjustment. Yeah. Exactly that. Same as in the traveling microscope, right? These just telescopes, right? After adjustment, T is only responsive to T means telescope, right? T is only responsive to parallel light. T is only responsive to parallel light. After adjustment, telescope is only responsive to parallel light. Underline parallel light. Underline parallel light. Okay? Right. So you have to make sure that this telescope only responds to the parallel light. Parallel light means what? Light coming from infinity. You have learned that those in optics, right? Light coming from infinity, those are parallel light, right? Parallel light beams. So the simple A, under adjustment telescope, we have subunits. Those subunits also should be done in order. So the first adjustment of the telescope. Telescope also have subunits of adjustments, right? So the first adjustment is, so remember that we have to make sure that this only responds to parallel light. The first sub adjustment is you have to adjust the distance between eyepiece and the cross wires. So we'll call that simple A, right? Eyepiece and the cross wires. You know, you can actually move these by hand. You can change the direction. Looking through here like this, you can change the distance between crosswire and this. Okay? Then what you would see? Through here you see this one. We call this view field. You have to change this distance till you see these crosswires clearly. You only see these crosswires clearly. You have to change this distance. You can move this by hand actually, right? By hand. Looking through here till you see clear crosswires through this view field. Got it? Through this view field. So that is the first sub adjustment of the telescope, right? Quickly take this down. Quickly take this down. And once you take this down, thumbs up. This is the same telescope as in the traveling microscope, right? There's no difference. There are 3 pipes, right? Okay. If you are done, thumbs up. If you want, you can name this. This is objective lens. This is eyepiece. This is crosswires, obviously. Whole thing is the telescope, right? This whole thing is the telescope. First adjustment is between crosswires and eyepiece till you see clear image of the crosswires. If you are done, thumbs up, right? Quickly take it down. Right. Below this, right, take down this note, write down distance between eyepiece and cross wires, eyepiece and cross wires is adjustable because least distance of distinct vision least distance of vision least distance of distinct vision is different for each observer is different for each observer. Got it? So the manufacturer of the spectrometer could have fixed this length, right? Could have fixed this length, but they have given us the opportunity to change the distance between crosswire and eyepiece. Why is that? I think you may have learned that many of you capital D, that is least distance of distinct vision. You know that from observer to observer, from student to student, this value is different, right? Usually this value is 25 centimeters. This is the distance that you form the final image, distance from the eye. So that is about 25 centimeters average value. But from person to person it changes, right? So you would have to change this gap depending on the observer, right? If you didn't understand, it doesn't matter. If you have learned that, if you have learned optical instruments, you will understand that. So you know that D value is an average value, that is a 25 centimeters. That is the least distance we can observe objects clearly. So when an object comes towards you, this distance is about 25 centimeters. If you bring it more closer than that distance, that image gets blurry, right? It gets blurred. So that is what least distance of distinct vision. So from person to person, it is different. That's why this distance is adjustable, right? Okay, so this is the first sub adjustment of the telescope. So we have to do this first. You cannot do this for the second part, right? You have to follow this order. Okay. Then we didn't adjust the objective lens. The distance between objective lens and the cross wires also should be adjusted, right? Actually, to do that adjustment, there is a knob. You can rotate that knob and do that adjustment. Okay, this is how we do that. Before that, I have to tell you that you might not see cross wires like this line vertical and this line horizontal. When you observe through here, you might see it like this. It is tilted, right? Then what do? Actually, you can rotate this by hand and make these cross wires vertical and horizontal, right? You can rotate this by hand. There are grips around it. Holding from that grip, you can rotate that. Looking through here, till you see this becoming vertical and horizontal, the cross wires. You can draw this below that. A complete note is given in the PDF, right? You can just draw this one. You can tilt it. Do this by hand, looking through the this eyepiece. Just draw this. Okay. Then simple B. Simple B means you have to adjust the objective lens actually. Distance between objective lens. right? If you think about here, parallel rays, parallel rays coming from a distant, from infinity, gets converged to a point here. Actually, that point is the focus of this objective lens. Focus of this objective lens, right? Parallel rays gets converged to this focus. Focus here. Got it? But the what we have to do is you have to move this whole part so the crosswires will be on this focus. So that is the another adjustment. So the crosswires here. Eyepiece here. Then what do you see? These parallel rays coming from here converged onto the crosswires. Then gets incident here, then here. When you arrange it like this, now the view field, you are looking through here, right? By rotating this, you can change this distance. When you look the view field, what do you see? So let's say you observe a distant tree. Distant tree means the tree is at infinity. A tree is at infinity. So in the lab, you can use through a window, you can focus a tree, right? Through a window. I mean, you can rotate this telescope. Usually telescope and the collimator are facing each other, right? You can rotate the telescope and point towards a distant object. After that, you do this adjustment till you see a clear image of a, let's say, distant tree. It can be any object, let's say a distant tree. So on the view field, you see an inverted image of the tree, right? You know that real images are inverted here through a telescope. So till you see a clear image of a distant object on the crosswires clearly, you have to adjust this knob. So this distance will be changing. This distance changes, right? So this is the second adjustment. So this is the second adjustment. Now what do you see? Now these rays are parallel rays. So now the telescope responds only to parallel rays, right? Only parallel rays creates the image. So this is only sensitive to the parallel light, right? Now the adjustment is complete. Okay. Draw this one. If you have drawn that, thumbs up, right? Have you drawn that? If you have drew that, thumbs up, right? Previously you drew this. You only have to draw this one, right? Okay. Below this, write down. Now the telescope is only responsive to parallel light, parallel light. Okay, parallel light. Telescope is only responsive to parallel light. Meaning now this only responsible to parallel light means now it is fully adjusted, right? Telescope is adjusted. So now you have to understand why do we do this as first step and this as second step, right? Before taking this image onto the crosswires, you need to see crosswires, right? First you need to clearly see the crosswires. Then only you can take the image onto the crosswires, right? So these two steps should be in order, okay? Without seeing crosswires, you cannot take the image to the crosswires, okay? So those two are the adjustments, sub adjustments for the telescope in order. Okay. Then collimator adjustment. Then write down the topic. See collimator adjustment. Collimator adjustment. Okay. Listen carefully, right? Listen carefully. Now you know that the telescope is only responsive to parallel light, right? So you have this telescope. It is adjusted now, right? The telescope is adjusted. It is only responsive to parallel light. Right? So from the collimator, what do you mean by adjusting the collimator? Adjusting the collimator means the collimator should only produce parallel light. Got it? Parallel light means all the light rays coming from the collimator should be parallel to each other. So you can send those light beams into the telescope. Understood? So that is what we call by adjusting the collimator. The collimator should only produce parallel light. Under this collimator adjustment, write down after adjustment, collimator after adjustment, comma, collimator should only produce parallel light. After adjustment, collimator should only produce parallel light. Okay? So I told you about the collimator, right? Earlier a little bit. So collimator is also just a pipe, like the similar to telescope. This pipe contains a small opening, thin opening, we call this slit. So when you look from this side, you see something like this. And there's a knob here. By rotating the knob, you can change the thickness of that opening, right? You can change the thickness. So this also is two separate pipes, right? One pipe which includes the slit and another pipe which includes a lens. Another pipe includes the lens, just a one lens. So these two can be moved independently. For this as well, there's a knob, right? A large knob. You can rotate that. You can change the distance between the slit and the lens. So through this lens, through this slit, there's a light beam coming like this, right? Light beam through a small slit, light beam comes like this, right? A light beam comes like this. So this lens, by changing the distance, if this is the focal length of this lens, you can actually produce parallel rays. If this is the focal length of this lens, you can create these parallel rays. You understand that? If a diverging light rays comes like this, and if you have a lens here, converging lens, given that the light rays goes through the focus of this lens, after the refraction from the lens, those light rays would be parallel, right? Okay. So by changing these two, the distances, you can produce this parallel light. You can produce the parallel light. So how do we know that this has produced parallel light? You see that you need to see this. So that also should be observed through the telescope. So everything you are doing everything. You cannot see these rays you cannot see, right? Everything is observed through the telescope. Everything is observed through the telescope. So if you see a thin image of this slit like this, meaning of that is these light rays from the slit, parallel light rays comes through the telescope to create this clear image of the slit, right? So for the collimate adjustment also, to check whether the collimate is adjusted, you have to observe through the telescope to check whether the collimate is adjusted. So now you can clearly understand why should we do the telescope adjustment first, right? Right. Draw this one. Take down this. There's a light source as well, right? This could be a monochromatic or a white light, uh, depending on the experiment. There's this light source. Then the collimator. This is the telescope. Take that down. Okay. So now we have adjusted the collimator. Now you can understand why telescope adjusted first, right? Because we use telescope to check whether other things are adjusted, right? Whether the collimator is adjusted. That's why we had to adjust telescope first, right? Right. Then the third one, write down level in the prism table. Level in the prism table. Third part, level in the prism table. Capital P. Level in the prism table. Okay. So the prism table is something like this, right? You just have a plate like this, just a plate. And below that plate, you have 3 screws. You have 3 screws like this. Goes through here and comes out like this. So these points of the screws are in an equilateral triangle. Then above this, there's another circular plate. So you can place this plate on those screws. There are 3 dents as well, right? There are 3 dents. So you can put these 3 screws like this, right? You can place this plate on top of these screws. There are 3 dents, so this plate wouldn't slip off, right? So you can just place it here. Then by rotating these screws, can you understand, like the you can those 2 plates are like this, right? By rotating the screws, you can change the orientation of the above plate like this. You can change, right? So these dents are in an equilateral triangle actually. Equilateral triangle. Quickly draw this one. Equilateral triangle. Clearer images on the PDF, right? So these are equilateral. This is on in an equilateral triangle. Quickly draw that. Okay. Below this right, after leveling the prism table, after leveling, comma, prism table and rotational plane of telescope. Prism table and rotational plane of telescope should be parallel. Okay. So what is this rotational plane of telescope? Okay, now I only draw one plate, right? But there are 2 plates here. So this is the simple sketch. You have the telescope here. To the telescope, then you have the collimator here. Collimator here. You can draw this with me. Here you have the prism table, and then you have the telescope. Then here you have the collimator. Collimator, telescope, and the prism table. This is the right. So the thing is, you have to level this prism table. Leveling the prism table does not mean you have to make it horizontal. It does not mean making it horizontal, right? You can easily make it horizontal by, if you have a spirit level here, You can easily make it horizontal, but it is not what we are going to do here. So this is the most important part here, right? Leveling the prism table. They asked many questions from this. Leveling the prism table means the prism table and the rotational plane of telescope. You know that telescope can be rotated like this, right? So the rotational plane of telescope is like this. This is what we call rotational plane of telescope. That plane is not visible, right? But that is the plane that the telescope rotates like this. Once you level the prism table and the rotational plane of telescope should be parallel. Should be parallel. That's the requirement, right? So this is rotational plane of capital T. So that is the what we call adjustment of prism table, right? So that is the requirement. I didn't explain how to do that. First you have to understand what it means, right? Then I'll explain how to do that. So if someone asks what is the leveling of prism table means? Leveling of prism table means rotational plane of telescope and prism table should be parallel. So that is the leveling of prism table. Done, right? This one? Taking it down? If you are taking it down, thumbs up. Just quickly take this down, right? The clear images on the PDF. Thumbs up if you are done. Okay, did you draw that? Right. So the leveling of prism table means the prism table and the rotational plane of telescope should be parallel to each other. So that is the goal here. That is what we are going to do. Right. So to do that, we need to use a prism. Now we are going to use a prism. You can take this with me. You place the prism like this on the prism table. So we call this prism table because we place the prism, right? 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 You place a prism on this prism table. So that is the first step. So that is the first step. Then you look from above. So the image I am going to draw is when you see from above the orientation of the prism. Then there is a special way. Now listen carefully, okay? Special way that you have to place this prism on the prism table. There's a special way. Listen carefully, right? Okay. So this is the prism table. So you know that these are the positions of screws. Let's say S1, S2 and S3. These are the three positions of the screws. Remember? Those positions are actually marked, right? Let's say the center of the prism is, prism table is here. Center of the prism table, I'll say O. Center of the prism table is O, and the positions of screws S1, S2 and S3. Now you are given a prism, you have to place that on this prism table. So how do you do that? So this is the procedure, right? So for a prism, you have to get the refracting edge. Refracting edge means the edge which includes the prism angle, right? So for the experiment, just one side of the prism is roughened, right? So you clearly identify the refracting edge. This edge is the refracting edge. The refracting edge should be closer to the center of the prism table, like this. And one side of the prism should be normal to one of these line, S1, S2, or S1, S3, S2, S3. One of those lines, one of the edge should be perpendicular, right? Other point is this refracting edge should be closer to the center. So it is like this. Let's say this is S1, S2. So these are in an equilateral triangle, right? S1, S2, S3. Then let's say you place the prism like this. One side of the prism is perpendicular to one of these lines. I'll just take S1, S2 line, right? Should be perpendicular like this. So this is the roughened surface. Roughened surface. Understood? So let's say this is P, Q, R. So this is how you place it. Got it? When you draw this line, one side of the prism is perpendicular one of these lines of the screws. Those screws are in an equilateral triangle. So one side is perpendicular to the edge of the prism. One side of the prism. It can be any of these sides, right? It can be either PQ or PR, but I placed it as PQ. So that is the first requirement. Perpendicular and center near the refracting edge. So those are the first requirement. So P close to center, and you can write this PQ perpendicular to S1, S2. So that is the first requirement when you are placing the prism, right? Then the second one, I'll say that before that just take this down and thumbs up, right? They ask many questions from this, right? So I have to understand, and if you have any problem, let me know. Just take this down and thumbs up. Right, so the first point, P close to center O and PQ perpendicular to S1, S2. Take it, write that down, first point. Then the second point write down, by rotating prism table, by rotating prism table, by rotating prism table, light from collimator, light from collimator should be incident on both surfaces of prism, both surfaces of prism symmetrically, both surfaces of prism symmetrically. Okay. Now you rotate this prism table, right? Now you rotate the prism table, then you will see something like this. You rotate this. So you have the collimator here. So from the collimator you get parallel light, right? From the collimator you get parallel light. So let's say center is here. You don't touch the prism now, right? You have already placed the prism. Then you rotate the prism table. You can rotate the prism table, right? Then the prism also turns with the prism table. And it would have an arrangement like this. Got it? Now the S1, S2 lines also gets rotated. Let's say it is like this. S1 here, S2 here. Still perpendicular, right? S1, S2, then S3 here. Now that is the next requirement. The light coming from collimator is incident symmetrically on both sides. Then this light gets reflected. You know, this is a partial reflection actually. Part gets refracted into the prism, but about 20% gets partially reflected, right? Then you can rotate the telescope to this position and catch this light ray. So let's say that is T1, position T1. So when you look through here, what do you see in the view field? You need to see a slit, image of the slit through the view field at this location, right? You might see this like this, right? Not horizontally, it is like moved upwards a little bit, like this, right? You have to make it symmetrical around this crosswire. So I have to move it downwards, right? You can do that by rotating these screws. You only rotate either S1 or S2. You don't rotate S3, right? I'll explain why that is. First, you either rotate S1 or S2. Then you can bring that image downwards a little bit. So it is something like this, right? So this acts as a mirror. This side of the prism acts as a mirror. So if a light ray comes like this, right? Let's say this is a mirror. This is a mirror. Light ray comes like this and gets reflected. If you rotate the mirror like this, right? If you rotate the mirror like this, that image goes up or down. But if you rotate the mirror like this at the same place, the position of the image does not change. Position of the image does not change. If you rotate the mirror like this, position does not change, right? Because the light ray would come like this and gets reflected. But if you change it like this, then the position of the image would go up or down. Same thing happens here. If you rotate S3, this edge would get tilted like this at the same place. The position of the image does not change in that case. But if you change either S1 or S2, rotate S1 or S2, these sides gets rotated like this. Then you can make this arrangement into symmetrically like this here. Right? So the first step is you have to rotate either S1 or S2. Either S1 or S2, not S3. Right? That's why we do that. So S1, S2 is perpendicular to this edge. You rotate either S1 or S2 in order to make this symmetrical like this. Right. So let's say you made it symmetrical. Then you know that this ray coming from the other side of the collimator also gets reflected like this. You can rotate the telescope to this side and catch that ray. Now you will see a view field like this. Still it is not symmetrical, right? It is not symmetrical. Then you don't touch S1 or S2. You have already adjusted S1 and S2, right? If you rotate S1 and S2, this orientation changes. So you are not going to change S1 or S2, right? You have a remaining screw that is S3. So once you take this to T2 position, you change S3, not S1 or S2. You rotate S3. Understood? Then you can make it symmetrical like this. You can bring this downwards. If it is not symmetrical, you can bring it down like this. Now we can make sure that the prism table is leveled, right? Okay, take this down, and once you've taken it down, thumbs up. Okay, below this, write down at T1, at T1, rotate either S1 or S2, either S1 or S2 till the image is symmetrical. Till the image is symmetrical. At T1, rotate either S1 or S2 till the image is symmetrical. Till the image is symmetrical. Another point, move the telescope, move the telescope to T2 position, to T2 position, comma, only use S3, only use S3 if the image is not symmetrical, if the image is not symmetrical. Okay, if the image is not symmetrical, right? So now we have fully adjusted the spectrometer. We have adjusted the spectrometer, right? So first we did the telescope adjustment. For the telescope adjustment also it had, first we adjusted distance between crosswires and eyepiece, then distance between eyepiece and crosswires for the second part. So we completed telescope adjustment. So that is the first adjustment. Then we adjusted collimator. Collimator adjustment means distance between objective lens and slit. After that, you would see a clear image of a distant object on the crosswires. Then we can say the telescope is fully adjusted. I mean telescope and the collimator. So once the collimator is adjusted, you see a clear image of the slit on the crosswires. Once you finish both telescope and collimator adjustments, then we did the prism table adjustment. So that is what we just did. Now the spectrometer is fully adjusted. So once we adjust that, now you can take readings. Reading means you can measure the angles between light rays using the spectrometer. Under this, write measuring an angle. Under here, write measuring an angle. Measuring an angle. I'll explain this using an example, right? Let's say example 1. So on the spectrometer, you have the main scale, right? Let's say 0 is here. Here you have 90 degrees. You can draw this with me. 0, 90 degrees, 180, 270 degrees, and again 0 and 360 are the same place. So this is the main scale. Right? Main scale. Then you have vernier scale. Actually, 2 vernier scales. In the spectrometer, you have 2 vernier scales. You separately measure angles from right vernier scale and then the left vernier scale. Left vernier scale is like this. Right? You take measurements from right vernier scale and left vernier scale separately, and you can take the average. That's the only reason it is there. So when you rotate the telescope, right? Remember the collimator is fixed to the stage, but you can rotate the telescope. So as you're rotating the telescope, the main scale is attached to the telescope. So when you are rotating the telescope, main scale rotate with it, right? So you using this one, you can measure how much is the rotation angle of telescope, right? So you can observe from here. So let's say you have a position of the telescope here. You have positioned the telescope here. Then you can get the reading. So let's say this is position of telescope is T1. For the T1, let's say what's the right side vernier reading for the T1. So it is about 105, right? It is beyond 90 degrees. So let's say it is about 105 degrees. Actually, you can read up to minutes, 105, 12 minutes like that. But for the simplicity, I'll only include degrees. So the T1 position, it is 105 degrees. From the right side, you read 105. From the left side, let's say you read about 285, right? 285. So that is for the T1 position. Then let's say for a different position, you move the telescope like upwards. You can draw this with me, right? So this is the T. So you have 0 here, 90 degrees, 180, 270. Again 360 here. Now let's say T2 reading is 40. For this position, reading is 40 from the right side. So 40 is about somewhere here. So we have the vernier scale. Then 180 degrees apart, we have the another vernier scale. So this is right side, this is left side, left vernier. Let's say then the telescope is somewhere here because it is rotated now, right? So for the T2, this reading is about 40 degrees. So from the left side, you can just add 180 to this one. So you get 220. You don't get 220 exactly, right? From the other scale, you get a different value for the left reading. Different value means it can be changed by a few minutes, right? But for the simplicity, I took it as, I just added 180 here, right? Then we can say angle measured by right. So you can separately find that angle measured using right scale. So for right scale, for the T1 it is 105, for the T2 position it is 40 degrees. If you take the difference of these two, you can take the angle that the telescope rotated by using right vernier scale. So 105 minus 40. So what's the value? It's about 65 degrees, right? So this is using right vernier scale. Then we get angle measured by left vernier scale. So what is that? It is 285 minus 220. So we got for that as well 65 degrees. Usually we don't get exactly same answers, right? because when you're doing the experiment, the values could be changed by a minute or two. It doesn't matter, right? Then what do we do? Therefore, we can conclude angle measured is equal to, you have to take the average angle, 65 divided by 2, right? So you have to consider the average angle, that is the angle correctly measured using the spectrometer. Take this down and thumbs up once you're taking it down. Okay, so at the last class we discussed how to adjust a spectrometer, right? So adjusting telescope, adjusting collimator, then finally adjusting the prism table. So once you adjust all those, the spectrometer is ready to get uh, angles, to measure angles. The spectrometer is ready now, right? Then we discussed how to get a reading, how to measure an angle using the spectrometer. So that is discussed under example 1. So from that point, today we'll be discussing the remaining part. So before that, I'll discuss one more example. Let's say example 2, right? Write down example 2. So this also is about taking a reading, right? In front of this, write, if 0 of vernier, if 0 of vernier passes, if 0 of vernier passes 0 of main scale, 0 of main scale, right? Okay, so just draw this with me. So this is the case, right? Draw this with me. So this is the prism table and the main scale, right? So here you have 0, 90 degrees, 180 and 270. Again here 360. 360 and 0 is at the same place. 360 and 0 degrees is at the same place, right? Then the let's say telescope is somewhere here. So this is the T1 position of the telescope, right? T1 position of the telescope. And the right vernier scale is somewhere here. So let's say it reads 15 degrees. So this mark is at 15 degrees. So, okay. So this is right vernier scale. Then apart from 180, another vernier scale is there. And it is like this. Okay. So this is regarding T1 position of the telescope. You know that with the telescope, main scale rotates, right? Main scale rotates. So this is for the T1 position of the telescope. Then let's say when you are getting a reading, you turn the telescope from this place to this place. Let's draw for that one. Again, 0, 90 degrees, 180, 270, and here 360, right? For the other reading, let's say for the T2 position, right scale reads 330. So 330 is somewhere here, right? 330 is somewhere here. So that is for the right scale. Then apart from 180, there's the another vernier scale. So 330 is like this, 0 of the vernier. Then here you have the left scale. For the left scale, let's say it is about 150, right? Then the telescope will be somewhere here. This is the T2 position of the telescope. So this is for the T1 position of the telescope, these readings. This is for the T2 position of the telescope. You can see the telescope is rotated, right? So with that, main scale also rotates. Right. Quickly draw these two, and once you finish, thumbs up. Right. So I'll put these values in a table, right? So for the T1 position of the telescope, T1 position here, T1 position this one, for the telescope, from the right scale, you can read about 15 degrees. Let's say here it is about 15 degrees, right? From the right scale. From the left scale, the difference is 180. So when you add that, left scale reads about 195 degrees. Okay, so these are just examples. Actually, there should be minutes values as well, but for the simplicity, I am not including minutes. Okay. Okay, so these are the two readings from the right vernier and left vernier for the T1 position of the telescope. Then you move the telescope to this position. From the right scale, let's say you read 330 degrees. For this one, you read 150. So you can see it is 180 degrees apart, right? Take this table down. Right. Then you can write angle measured by R for T1 position. What should it be? For T1 position, no, angle measured by right vernier. Using the right vernier, if you measure the angle means the angle that you rotate the telescope, right? From here to this position, you have to rotate the telescope. So here the angle measured from right vernier is what? From the right vernier, it is 15 degrees, right? From the right vernier, angle measured here is 330. So you have to subtract those two values to get the angle. So what do you get? You get 315 degrees. You get 315 degrees. So what's the problem here? You only rotated the telescope by a small amount, right? From here to here you rotate it. So when you are doing the experiments, You don't measure angles like this. So so the measured, actually what you have measured is this angle, right? It is not the angle what we need. So if you get a large angle like this, which is not possible, what should be the angle? Correct angle. To get the correct angle, you just subtract the values, but then you have to subtract that from 360 degrees. Understand that? This is the angle, right? But from the vernier, you got 315 degrees. In order to get this theta, you have to subtract 315 from 360. 360 minus 315. So it is, I think, 45 degrees, right? So 45 degrees is the correct angle. So whenever you get a large angle like this, you might get questions like this, right? If you get a large angle like this, if it seems not possible, just subtract that from 360 degrees. Then you get that small angle, right? So that is 45 degrees. So this is measured using right vernier scale. Then angle measured by left. Okay, left means this one, these two. So we have two angles. For T1 position, you read 195. For T2 position, you get 150. Here 195. Here you get, from the left side, you get 150. So when you subtract that, you get the same angle, 45 degrees, right? So both right and left vernier scales should read the same angle, right? Same angle. Because both are rotated by the same amount of angle. You read the same angle, right? But you don't get the exact values like this, right? The values you get may different by a few minutes. But this is for simplicity. So the what do you get? You get the average angle. So what's the average angle? 45 plus 45 divided by 2. So that you get 45 degrees here. Right? We do this for the accuracy, right? To increase the accuracy, we read the angle from right vernier, then we read the angle from left vernier. You get two values. Then you get the average. So that is more accurate there, right? So you know whenever you get right and left sides, I mean more than one, and take the average, it is more accurate, right? Okay, take these two down. So this happens when vernier scale has passed the 0 mark. Okay, simply whenever you get a very large angle that is not possible for the experiment, just subtract that from 360. That's all you have to remember, right? Okay, if you are taking it down, thumbs up. Right. So this is how now you know how to measure any angle using the spectrometer, right? Then we'll discuss about least count. Least count means the minimum value that can be measured using a spectrometer, right? Write the subtopic least count of spectrometer. Least count of spectrometer. Okay. So when you take the spectrometer, 29 main scale parts is divided into 30 vernier scale parts. Okay. 29 main scale parts divided into 30 vernier scale parts in the spectrometer that is available in the lab, right? And also uh, main scale is in half degrees, right? Least count of the main scale is half degrees. Least count of the main scale, it is not 1 degree. That 1 degree also is divided, is split into 2. So the main scale least count is half degrees, right? So how do we find the least count? Least count, what do we call? Main scale part minus vernier scale part. Difference between main scale division minus vernier scale part. That is how we find the least count. So the main scale, one part of the main scale is 1 over 2. 1 over 2 degrees, half degrees, half of a degree. For the vernier scale, it is, how do you find that? 29 parts is divided into 30. So 29 main scale parts, 29 main scale parts is divided into 30. Correct? So the one part is half a degree, right? So the angle here is half a degree, 29. 29 half degree parts in the main scale is divided into 30 vernier scale parts. So from this one you can get the length or the angle of a one part of the vernier scale. Okay, then you can take this half out, half degree out, then you get 129 over 30. Half degree 1 minus, so you get when you take the denominator you get 39 minus 29, 1 over 30. Half degrees times 1 over 30 is what? 1 over 60 degrees. 60th of a 1 degree. What is that? It is a 1 minute, right? 1 minute. So you can see, using the spectrometer, you can measure up to 1 minute. So that is the least count. Okay. Take it down. Take it down and thumbs up. Right? So this is how you find the least count of the actually any measuring instrument, right? So you have to know that for the spectrometer, you can accuracy is up to 1 minute. 1 minute means 1/60th of a 1 degree, right? 1/60th of a 1 degree, right? Okay, now we know everything in order to do the experiments, right? Right. So for the 29th experiment, so once you know all these, doing the experiment is easy. Once you adjust it and know how to take a reading from the spectrometer, doing the experiment is easy. You just have to take the measurements, right? Right. So this is how you do the experiment. Actually, this is 29th experiment. In that experiment, we have to find refracting angle or prism angle, right? Write the topic finding refracting angle or the prism angle, we call that prism angle. Write the topic. Okay. So here you have the prism table. This is the prism table. You get the prism and at the center you just place the prism like this. You don't have to follow the previous, remember when you are leveling the prism, you have to follow some steps, right? to level the prism table. Here you don't have to, right? You already have leveled the prism table, so you don't have to level it again, right? So you just place the prism like this. Only requirement is, so you have the collimator here. So from the collimator, you have parallel light coming from the collimator. Only requirement is this parallel light has to be incident on the prism symmetrically, right? So what happens is when the light is incident here, it reflects off like this. There's light refracting into the prism, but we don't consider the refracting, right? Here we take reflection of rays. So to identify this ray, you have the telescope. You can rotate it around this to identify these light rays or the images formed. Okay. So you bring the telescope here. Okay. So this is, let's say this is T1 position of the telescope. Let's say you see the slit, you know that slit, image of the slit like this. Now it is symmetrical, right? Because we have already leveled the prism table, it is symmetrical now, right? Everything is clear now. But the slit is slightly somewhere here, right? So when you get the image of the slit, you have to keep finding for the image of the slit, right? By rotating. Let's say you get a position like this. When you get a position like this, you lock the telescope. There's a screw, right? Then there's a knob at the side. You find, once you lock it, then you can fine adjust using that knob. And you can move the telescope slightly to this side. And what happens? You know the rays here, you can further rotate it slightly to this side, right? Then the image of the slit moves to this position, like this. So once it is moved to this position, now you take the reading. Now you have the right vernier scale and left vernier scale. From both, you take the reading. You measure that angle, right? Let's say you got that angle as θ1. Okay, that is done. Now you have the value of that angle. Not an angle, just the reading here, right? Then what do? Then you move the telescope to this position till you find the image of the slit. Again, you might see the slit like this. It could be here or it could be here. Then you fine adjust till you get the image right on the crosswires, right? So this is the T2 position of the telescope, and let's say you measure the angle as θ2. Actually it is not an angle, it is just a reading, right? From the left and right, from the left vernier and right vernier, you take the measurement and take the average. That becomes the θ2 value. θ2 value. Right. Then what do? From the difference of these two angles, you can measure this angle. So in theory, you know that this angle is twice as the prism angle, right? This angle is twice as the prism angle. So now what can we say? θ1 minus θ2. If this is larger than 360, you can see it is not larger than 360, right? In the experiment. If you get an angle larger than 360, You just have to subtract that angle from 360. Let's say we didn't get a larger angle, like a reflecting angle. You didn't get a reflecting angle. You just get a angle that is less than 180. Large angle minus small angle. You need to get a positive value, right? So this is equal to twice the prism angle. So how do we find the prism angle? So A is equal to theta 1 divided by theta 1 minus theta 2 divided by 2. Right? So this is how you measure the prism angle. Okay. This is how we measure the prism angle, and take this down and thumbs up. Right. Here we use rays that is partially reflected, right? There are refracting rays. You know that the colors are divided, right from red to violet. Colors are divided, dispersed. We call that dispersion. Colors gets divided when it is refracting. When reflecting, colors does not get refracted. I mean dispersed, right? Here for this experiment we use reflection actually. We call this, there's a 20% partial reflection, right? We use a reflection. So for the light source, we can use either monochromatic light or a white light. It doesn't matter, right? Monochromatic means single color, meaning it is either red, blue, yellow, something like that. Monochromatic. In the experiment, if refraction is involved, you have to go for a monochromatic light. But here reflection is involved. So you can use either white color light or monochromatic light. It doesn't matter, right? Below this, write down. Below this, write down. Here, monochromatic light beam, monochromatic light source, monochromatic light source is not essential. Monochromatic light source is not essential since only partial reflection is used. Since partial reflection is used. Then the next point, to increase the accuracy of angles, consider average value, gained from R and L verniers, right and left, right? Gain from R and left verniers. Gain from R and L verniers. Then the third point, note that slit should be very thin. to get more precise readings. Slit should be very thin to get more precise readings. Right? So the last point I'll explain that. Let's say you get the slit like this, right? What happens now? You cannot know whether this is precise here, right? You might read the angle here or here or here. So you have to minimize that as much as possible. There's a limit you can make it thin, right? Because otherwise, no, you have to get sufficient amount of light through the slit. Otherwise, you won't see an image. But you have to make it as thin as possible, right? So the measurement, I mean reading, would be more precise, right? Because the variation is small now, right? So that is what the third point means. Okay. Then we'll consider how to get how to measure angle of deviation, right? Angle of deviation. Write down the topic measuring angle of deviation. That is simple D, not minimum deviation, just the angle of deviation, simple D. Okay? Right. So when the deviation happens, there's a refraction, right? So whenever there's a refraction, there's always a dispersion of light. The light gets separated into colors. So those color spectrum disturbs the experiment, right? So for this part, you have to use a monochromatic light. It is either red, blue, anything like that. Usually we use a sodium bulb, right? Which is yellow in color. So for the light source, here we use monochromatic, right? Then you have the collimator. Then here you have the prism table. Okay. So this is collimator. So here you have the telescope, right? Telescope. So align with this light ray, you have to fix the telescope here. Okay. We haven't put the prism, you have removed the prism, right? You need to get this reading. So the light rays goes like this directly. So how do you know whether you don't see these light rays, right? All you see is in the view field, you see this slit actually. Then you lock it here, the telescope, you lock the telescope. Then you fine adjust till you get the slit onto the crosswire. Right? You fine adjust till you get the slit, image of the slit on the crosswire. Then we can say all the light rays from here has entered the telescope and they are aligned. Right? Then what do? You take the reading. You take the reading of the related angle. Right? Let's say that is theta 1. Okay. Right? So that is the first step. This is the T1 position of the telescope. Then what do? We place, because we need to find the angle of deviation, right? Then we place the prism. Anywhere you like, you can place the prism here, like this, right? Prism like this, you can place it. Then what happens? So the light rays coming from the collimator is incident on this surface, and this is the angle of incidence, right? Angle of incidence is here. It is supposed to go to this direction, but due to the prism, it gets refracted. Let's say like this. Then again it refracts to here. So this is the emergent ray. So the angle between this ray and this ray is the angle of deviation, right? So to figure this ray, you have to move the telescope, rotate the telescope from here to here. Let's say here, like this. So this is the T2 position. Again, you fine adjust that till you get the image on the cross wires and get the reading, that is theta 2. Then what do? So D is equal to what? Theta 2 minus theta 1. Right? From the you always have to get the positive value, right? So you can see it is not possible for this to get like a reflective angle, right? This is an acute angle. So if you get a reflective angle, you have to subtract this value from 360 and get the angle of deviation, right? Angle of deviation, simple D. Okay. Take it down and thumbs up once you have taken it down. You can take this down as I'm explaining, right? Doesn't matter, but you have to pay attention as well. Right. So this is how you measure angle of deviation for any incident angle. For any incident angle, this is how we measure that, right? Okay. Then write the topic measuring angle of minimum deviation. Measuring angle of minimum deviation within brackets capital D. Measuring angle of minimum deviation capital D and simple n. Simple n means refractive index, right? Right? Measuring angle of minimum deviation and refractive index, simple n. Right? So similarly, we can find the angle of minimum deviation. But you have to recognize, only difference is you have to recognize where that minimum deviation happens. Okay? Right. So if you remember this graph from the theory, so from a small value, you keep increasing incident angle. So when you keep increasing the incident angle, what happens to the angle of deviation? This is not minimum deviation, right? This is deviation. Deviation rapidly decreases. And after minimum value, it starts to increase. So this is what we call angle of minimum deviation. So you know at that angle, I and R, those are say equal, right? Right. Not R, I mean I1 and I2, those are equal. But here you have to find minimum angle. You have to recognize when this happens, right? Similarly, you can do this. So how do we do this? you can rotate the prism table, right? You can independently rotate the prism table. So there's a screw, you have to loosen that screw, and you can start rotating this prism angle without slipping the prism, right? You have to slowly rotate that. If you quickly rotate that, this would slip. You have to slowly rotate this, right? Okay, let's see what happens. So I have to start from a small incident angle, right? See that? Small incident angle, right? So I have to, let's say you have to rotate this somewhere here in order to make this small. This I should be small, right? When you rotate it here, I gets small, right? Then you start rotate to this side. Once you take I to a small angle, you can start rotating prism table to this side, right? Now what happens? When you are rotating the prism table to this side, do you understand that with the prism table, this prism also rotates? This I increases, right? When you rotate the prism table here, this I increases like this. I increases. So when I increases, what happens to simple D? It decreases. See that? When I increases, simple D decreases. So I increases, simple D decreases. So you can see this ray is moving to this side. When you are rotating the prism angle, prism table, let's say this is like a mouth. This mouth is closing, starts closing. So you have to follow this slit. Slit starts to move to out of this view field, right? Out of the view field. So you have to follow. So this ray is getting like this. You have to follow that using the telescope, right? So let's say this is the cross wires. Initially the slit was here. Then let's say slit moved to this position, right? This position. As you are rotating the prism table, the slit moved from here to here. Image of the slit. Let's say after this position, right after this position, slit starts to move to the opposite direction. You have to identify this position, right? Right after this position, the slit, image of the slit, starts to move to opposite direction. Why is that? After this point, further increase of I causes D to increase now. Now understand, initially this ray is moving to this side, right? Move to this side. But when you further keep rotating the prism table, D starts to increase. Then initially the ray was moving to this side. Now it starts to move to other side, opposite side. Then that is what you see. The slit starts to move to opposite side. You know that starting position happens at the D minimum value, right? Then you have to identify this location, and you stop the telescope. Then you adjust till you get the image of the slit onto the cross wires, right? So it's here, it starts to move to here, then you get it to the cross wires. Then take that reading, let's say theta. So that is theta. Then D should be what? Theta minus T1. You just take the difference, right? Large angle minus small angle. So D is theta minus theta 1. So that is the angle of minimum deviation. So that is the only thing that happens, right? This slit starts to move to opposite side. The starting position is related to this minimum angle. Understood? Right. That is all you have to do. So at that point, you have to stop moving the prism table, right? Then you have to follow using the telescope. Right. Draw this one and draw this one as well, right? This one as well. Then write this equation. Right. You can refer this again, right? The more you refer, the more clearer this will get, right? Okay. So now we have measured the prism angle and angle of minimum deviation. Prism angle and angle of minimum deviation, right? Then you can find the prism material. So you have this equation divided by sine A over 2. So A is known, D is known. You just have to substitute these values and simply you can find the refractive index of the prism material. That's all you have to do, right? You can simplify the refractive index of the prism angle, prism material. Write that equation down. Here, you must use monochromatic light, right? Monochromatic light you must use because there's refraction. Sorry, there's dispersion because due to the refraction, right? So for this experiment, you have to use monochromatic light. Okay, monochromatic light. Take that equation down and you can find that using that equation, you can easily find the refractive index. Okay, so spectrometer practicals is one of the most important, right? And many students have misunderstood this experiment. They frequently ask questions from that. I'll send the past paper years that they have asked questions onto the group. Then you can do those questions and practice. So once we finish that, refer the experiment again, the note I have given again, and you can refer the PDF as well, right? So that is a detailed PDF, and do the questions. Do the past paper questions, and that's all, right? Then you can have a in-depth understanding of spectrometer, and you don't have to worry about spectrometer again, right? Right. I'll send the past paper questions, and we'll wind up the spectrometer part here. And tomorrow there will be a class at 8 p.m. around 8 to 8:30 to discuss how to find the focal length of a convex lens and a concave lens, right? So once we did that, all the practicals in once we do that, all the practicals in light optic parts are covered, right? Okay. So we'll see you tomorrow at 8 p.m.